This is yet again work done during my internship this summer at AWS, this time with Stefan and Olivier. It is on a benchmark translating MiniF2F, a math benchmark, into Dafny, and then checking how well does LLM-guided mathematical proof synthesis work in an autoactive verification domain. So since the audience, I assume, is mostly into autoactive verifiers, I'll do a background slide on MiniF2F. MiniF2F is a benchmark released by OpenAI in 2021. Originally, it was in Lean 3 and Metamath, partially in Isabelle and HOL Light. Those translations have then been made full, and then later translated into COC and Lean 4 when that came out. It is composed of nearly 500 problems, split in equal to test and validation set. It is sourced from the International Math Olympiad, AMC, AIME, and other competitions, as well as undergraduate curricula. The reason why I'm even talking about it is that it still is, and definitely was, the de facto standard mathematical benchmark for neural reasoning in interactive theorem provers since its release to 2025. So just to get a sense of what this benchmark even is, here's an example problem. In natural language, the problem is the following. You have a set of positive integers, a, b, then their difference, then their sum, assumed to be all prime numbers. And then you're given the multiple choice question of if the sum of these four numbers is one of the following. And this presents a bit of a problem, like how do you formalize this? And at the time, in 2021, the sort of way to formalize this, or the natural way people did it, was they picked the answer and they formalized it as sort of an unfaithful translation without having to guess the answer. So the benchmark is formalized in this way, and this follows for IMO problems and such. As I was mentioning, originally it was in Lean 3. And this is important because if we go and look through the times in history, and I've chosen to count today in times of popples. So starting from popple 2023, this was a benchmark in Lean 3 at the time, and there was some preliminary work on the benchmark with neural models trained primarily at OpenAI, scoring at first just under 30% and then around 40%. And this 40% number, let's keep this in mind, but there was some work being done training models of GPT-3 scale, trying to do neural theorem proving in Lean, and the performance was around 40%. Now, I was definitely not around at popple 2023. Neither I was at popple 2024. And maybe that's a good thing, because the improvement on the benchmark didn't sort of really pick up. There was some work on evaluation of of language models in this domain, but interestingly, throughout this year, there was no real improvement on this benchmark. And then 2025, last year, already a massive amount of models dropped, and performance jumped to around 70%. So this is really the time when these models sort of got a lot more Lean data and started auto-formalizing a lot more Lean data. And the final story of the benchmark is that in the summer of last year, this benchmark was saturated by Seed Prover, which is the source from where I took this this figure, reaching 100% performance on the test set, so solving all of the problems. And really, through the range of models that have been developed, this is really a vibrant field. And this benchmark in particular was the leading driver of that. So why the case for MiniF2F in Dafny? The sort of questions we wanted to answer are the following. Firstly, Dafny is known for its sort of easy verification of some of the code you're verifying. So we were just wondering, how does that stack up into a math domain? How can we compare SMT-based automation in Dafny to automation in ITPs such as Sledgehammer and Isabelle, Grind and Lean, and similar? And then secondly, can we leverage neurosymbolic techniques to effectively generate mathematical proofs in an auto-active verifier? So switching domain from ITPs into Dafny here, and seeing how effective is this transition. And the contribution we have is the first translation of MiniF2F to an auto-active verifier, accompanied by a proprietary library, as well as a benchmark of a broad range of LLMs testing their abilities to synthesize proofs. While translating this benchmark, some translations were quite obvious and easy. So here's an example Lean 4 statement on the left. We don't need to look at the preamble, but if we look at simply the statement here, all of the lines more or less translate naturally to statements in Dafny. And then the way we state this, we state it as a lemma in Dafny. We have requires and ensures clauses, as is typical, and then we leave the proof as blank for the model to fill in or SMT to solve it automatically. And notice that we include our proprietary definitions and library. That's something I'm going to come back to. But not everything is so easy. Some translations were quite ugly, especially ones that leverage the mathematical library of Lean called mathlib. So there's a good reason for why import mathlib is there at the top of the file. And the reason for that is that once you have something like calling a square root on non-negative reals, or a filter, or a filter.addTop, you're obviously leveraging the library there. And in Dafny, naturally, because of the domain, we had to formalize this ourselves. So we stated it, but we had to make those definitions in our library. And these are the particular sort of predicates that we had to formalize. How do we do it? So in Lean, everything is foundational, and mathlib is derived from foundations. So the community does not allow for contributions that have partial completeness. However, for us, we didn't aim to redevelop mathlib from scratch. We don't think this is the notion of auto-active, this is not the standard in auto-active verification, nor for this project. We simply wanted testability, hence we axiomatized the predicates required to state these problems in the definitions file. So each of the predicates has the axiom keyword in Dafny, and this in particular axiomatizes limit definition. Whether this limit definition is actually workable in Dafny is to be seen. I mean, the triggers do trigger, but it potentially is requires a large library for this to be actually useful. So just to recap our approach, we defined all of the necessary concepts to define this benchmark. We introduced a compact library of just over 100 axiomatized lemmas. So neither for the lemmas nor for the predicates, we actually added proofs. But these lemmas are well-known facts, some translations from facts in mathlib about the concepts required to prove these problems. And then we prioritize capability over completeness. So we wanted to show to test whether it's in principle from these axioms possible to verify these statements instead of being complete here. And the big punchline at first, once the formalization, the translation was done, was that 40% of the test set were solved automatically in Dafny without a proof. Without an LLM-generated proof, that is. This number is actually higher even on the validation set, reaching around 45%. But if you remember, in 2024, in Lean, this was the state of the art. Training models of GPT-3 size. So we had, Dafny has something right. In Dafny, automation is powerful enough to handle 40% of these quite complex problems. And a particular success case that we were very sort of inspired by and just in general interested in was IMO 1095 problem 1. This famous problem is known to be as one of the easiest IMO problems because it's one of the first IMOs ever held. And here's a proof from the model that saturated the benchmark, seed prover. The formatting was fit to make the slide, but it's roughly like 15 lines of code. In Dafny, that's trivial. It's just an empty proof. The proof, as sort of is always is in the pudding. The way we axiomatize GCD has the required requires and ensures clauses to propagate the statement. However, this is really impressive. Synthesizing an automatically synthesizing a solution for an IMO problem without any particular tuning for the system. However, we have 40% of the proofs. We don't have the remainder. Another thing that we wanted to test was the compatibility of LLMs to automatically synthesize Dafny proofs in a mathematical environment. So we tasked LLMs that we could get access to synthesize proof hints and auxiliary lemmas to complete these proofs. We noticed that some of the proofs might be easier to modularize, so we allowed for auxiliary definitions, but we never allowed for the models to change the specification. So the requires and ensures clauses had to stay exactly the same. And we didn't allow for adding any axioms within the so we didn't allow cheating essentially for the models. We had 12 models benchmarked in total, and here are the results. In our methodology, each attempt here corresponds to the LLM iteratively attempting for 4 attempts. So that is attempting once, then getting error feedback from Dafny up to 4 times in that fashion, and then we ran up to 4 such parallel attempts. So the baseline on the left is around 40%, and we saw that the best model at the time of testing was Sonnet 4.5, reaching around 55.7% performance. So much lower and definitely not saturating the benchmark as in lean. However, still there were some inferences where the models helped push the automation over the edge. Some models are much worse. So interestingly, Haiku was only 44%. So just essentially a few problems over baseline. And the general gist of the models we tested was that they fell somewhere in the 50% bucket. So not a huge improvement, showing that these models were not really trained for this task in Dafny, however, showing some capability. How does this look like? An example problem where the proof doesn't get automatically synthesized is the following induction problem, showing that taking 4 to the power n plus 1 and adding 20 is always 0 modulo 12. So of course, on the left, I've shown in my editor that this doesn't pass the compiler, but on the right, this is a proof generated by Sonnet. Naturally, given it's an induction proof, the model splits it up into a base case of n equals 0, does the required assertions there, and otherwise calls the inductive step and generates the required assertions to prove it. So really, in principle, this is possible. However, due to limitations of the model training, both in Dafny and as well as our proprietary library perhaps being a bit too small, we didn't see performance matching the performance in lean. Just to recap the limitations, brittleness is still a huge limitation even when LLMs come into play. Minor changes in assertion order or even calc statements do change the cause of verification failures. The models might be changing, fixing one error that it got in a particular error correction run. And then even though the rest of the proof body doesn't change, another brittle error comes up afterwards due to the changes in the assertion order introduced in that way. So better error feedback and what we heard about a more stateful Dafny would definitely help here for the models to get better feedback from the system. Otherwise, we saw some syntax confusion. So models do tend to mix Dafny syntax with lean and conc. And I'm interested whether this is because the models were trained on a subset of MiniF2F code, so them thinking that this is mathematical theorem proving I'm doing, so I'm calling some lean definitions and lean lemmas. But in general, this is a huge limitation because the models might have the proof 90% correct, but if they call a given lean lemma, then of course you just you waste your attempt. And of course, our lemmas library might be expanded, and it would be interesting to track how that improves performance. So to recap, main takeaways. Firstly, Dafny's SMT's automation is very powerful compared to existing automation in other interactive theorem provers. Just to give you some numbers, Sledgehammer and Isabelle scores around 10% in MiniF2F, and the best numbers I've seen in lean, and there's a chance that it was optimized for lean, score around 27%. So Dafny still outperforms by quite a bit. Secondly, LLMs can be successfully used to synthesize Dafny proofs for complex math problems. And that's sort of a new finding we've seen. And then to leave you, we have two questions. So through our work, finding some IMO problems being solved with no proof at all, or no proof that we can read at all, and some proofs being quite verbose that are LLM generated. I think this poses a question: what proofs are best for researchers to interact with? Like, do we even want to see the proof? And I'm going quite aggressive here. And then what proofs are best to train models with? Of course, we want some interactive feedback. So if all of the proofs in Dafny are either empty or super long, that might not be good to train these systems as well. So just leaving you with a few questions. Thank you.
Time for one question.
Thank you. Yeah, that's very interesting. It's a very interesting experiment. I have a question about where did you draw the line, what to put as axioms into these files with definitions? I mean, you could have put the statements themselves, so yeah.
Yeah, so the lemmas I looked quite deeply into and thought that we need to axiomatize it in a way where the definition should be usable and be as close to be fully complete as possible. So for example, for the exponential function, you can think of it as you define it as 0, you define it to be continuous, and you define its multiplication to be additive. So like distribute over multiplication. So that sort of ethos was followed throughout the other definitions as well. In principle, from that, everything should be derivable. But of course, MATLAB is much more complete in this.
Let's thank the speaker again.